Hey YouTube, it's Roman. I'm back, and if you notice, today is a Monday, not the typical Wednesday we release content, and that's because today is the first official Math Monday. Math Mondays are going to be dedicated to the iPad and occasionally Overleaf to talk about different mathematical and statistical topics and their applications. And Wednesdays are going to be oriented more towards the programmatic implementation of the topics on Wednesdays, or perhaps independent topics altogether in Python, maybe even Java, C++, or R, depending on what you guys want to see. That being said, this first Math Monday is going to be dedicated to the normal distribution. We're going to be diving into statistics. If you are unfamiliar with the normal distribution, then I want to welcome you to the wonderful world of statistics. We're going to be covering one of the most widely used statistical distributions out there. And if you're not new to statistics, then hopefully this is a nice refresher for you. So what does the normal distribution look like? Well, a normal distribution is often referred to as a bell curve. And if we draw a normal distribution, you'll see how it gets its name. It actually looks quite a bit like a bell. So we have this bell curve, or this normal distribution here. And what this does is it defines a set of possible outcomes for some random variable. So it helps us model outcomes of a random variable. There are several moments or different measures of this particular distribution. We're only going to focus on two. That is an average value and a measure of spread from that particular average value. And these are the first two statistical moments. So the first moment is going to be the mean, or the average value. So on average, what value can we expect from this random variable that follows a normal distribution? That is actually going to be defined as the mean, which is typically referred to as mu, and you can plot this on this chart right in the center of the distribution as mu. It turns out that the normal distribution is actually defined in terms of the first and second moment. You need a measure of an average value, so in this case we have mu, and a measure of spread, which is typically variance. So if we wanted to say a random variable x was normally distributed, then I would use this tilde here and then say that it is normally distributed with an n, and it would be a function of mu and sigma squared. So mu and sigma squared, where mu is going to be the average value, the first moment, and sigma squared is going to be the variance, the second moment. Now, a more productive measure of spread is often standard deviation. Standard deviation is the square root of variance. So if we were to just take the square root of sigma squared, you see that we simply get sigma, and this is referred to as standard deviation. Now, the reason we care about standard deviation is because it tells us a lot about where outcomes may fall in this particular distribution. Specifically, this is called the empirical rule. If we add and subtract a standard deviation to and from the mean, then we end up with a new interval and a probability that an outcome of x is going to be within that range. So for example, if I was to add sigma to mu and subtract sigma from mu, then I would get mu plus sigma, mu minus sigma, and if I was to draw vertical lines up, it would create something like this, and we can say that an outcome of x within this range is going to occur 68% of the time. Now, the further we go out in this distribution, the less likely x is to take on the values within that range. So as you can see, the tails, as we call them, start to get smaller and smaller and smaller, implying that that particular outcome of x is less and less and less likely. So it turns out, just to hammer this point home with the empirical rule, we know that an outcome of mu minus sigma, mu plus sigma, will occur 68% of the time. An outcome of mu minus 2 sigma, mu plus 2 sigma, will occur 95% of the time. And an outcome mu minus 3 sigma, mu plus 3 sigma, will occur 99.7% of the time. This gives us a lot of information about the potential outcomes of random variable x. Now, I want to give a quick example using stock returns, but I do want to note that empirically, stock returns exhibit excess kurtosis, so it isn't really appropriate to assume that they follow a normal distribution, even though from a regulatory standpoint and in academia, it's often assumed, even inappropriately most of the time. Nevertheless, let's take a look at an example using stock returns. So I'm going to say that R is a stock's return. It's going to be distributed normally with a mean of 0 and a variance of 0.2 squared. Okay, so now if I was to plot this, we have our bell curve here. We know the mean value is 0, and we can go one standard deviation away from the mean in both directions and find where the return is going to be 68% of the time if it were to follow a normal distribution. So we know that the standard deviation is going to be equal to 0.2. So if we were to add and subtract 0.2 in both directions, we would just end up with 0.2 and 0.2. And you can assume, I'm sorry, this is negative 0.2, and you can just assume that this is an annual stock return for maybe a very volatile stock, because this is a 20% return or a 20% loss. But nevertheless, based on this distribution here, we know that 68% of the time, the return is going to be between negative 20% and positive 20%. Do keep in mind, this is of course assuming that the stock return follows a normal distribution. If the stock return does not follow a normal distribution, then in reality, this may be a very warped perception of the probability that the return falls between this range. Mathematically, we can look at the variance and the mean or the expectation of this stock return by saying E of R is equal to 0. That is by the definition of the normal distribution. We use the first two moments, the mu and the sigma squared. And the variance, so the var of R, is going to be equal to this guy, that is 0.2 squared. So we have the expectation and the variance, the average value and the measure of spread for this stock return that is assumed to follow a normal distribution. Based on this example, a very natural question arises. What is the probability of a particular stock return? And this brings me to some of the trickier parts of the probability density function and the cumulative distribution function for the normal distribution that we're working with right here. These are tricky topics, but I think we can cover them pretty effectively. The probability density function is going to give us the likelihood that a draw falls within the range of some given value. Now, the reason that I'm stating this so around the bush is because formally the probability of any one outcome in a continuous sense is 0. And I can just do a quick proof for you to show you why it's 0. If we were to draw this bell curve, then you'll notice that the domain of this function is negative infinity to positive infinity. We can effectively put in any value and get an outcome. Even if the outcome is extremely, extremely, extremely small, it's still defined. So the entire space is infinity. And one outcome is just one outcome. So the probability of any outcome, by definition, is going to be 1 over infinity. Now, I'm sure we don't want to sift through the calculus to show that this is 0, but if you were to try to divide 1 by infinity, or a very, very, very large number as infinity is usually defined by, we will end up with 0. So this brings up a very interesting theoretical and unnecessary question is, if something has a probability of 0, can it not occur? Now, instead of diving down this rabbit hole, I just want to instead define the probability density function and talk about the implications of why it's useful. But in a theoretical sense, just for those who are interested, the actual specific probability of any particular outcome of this continuous distribution is going to be 0, as seen by this kind of toy example here. The PDF is formally defined as little f of x, where x is essentially one potential draw from this normal distribution. So we have f of x is equal to 1 divided by sigma square root of 2 pi e to the negative 1/2 x minus mu divided by sigma. So this is going to give us the likelihood that a draw is within the range of a particular x. So if we were to do, for example, n is distributed by 0, 0.2 squared once again, and we wanted to say, hey, what is the likelihood that the outcome of a particular sample is going to be 0.1, then we would simply do f of 0.1, and we would say that this is equal to 1 divided by 0.2 times 2 pi e to the negative 1/2 x minus mu, which is 0, divided by sigma, which is just going to be 0.2, and this is going to give us that likelihood. The cumulative distribution function, the so-called CDF, is going to be defined by capital F of little x is equal to the integral from negative infinity to little x of f of s ds, where this f of s is the probability density function that we just defined. The cumulative distribution function is different from the probability density function in that it gives us the probability that x is going to fall within a specific range. That is from negative infinity up until a certain value. So graphically, this is going to be the area under the bell curve. So if we have negative infinity all the way out here, and we specify x to be some value maybe right here, right below the mean, then if we were to solve this integral, we would get the area underneath the curve, and that would give us the probability that an outcome of x falls within this range, this negative infinity to this little x value. Fortunately for us, most of the time, we actually don't need to go about solving this integral. We have a lot of numerical implementations in Python, Excel, etc. to solve this integral for us and come up with a probability for the CDF or even a likelihood for the PDF. So in general, it helps to note what the PDF and the CDF are and what they're doing, but we very rarely need to even specify a function to compute these values. Most of the time, they're already prepackaged for us in whatever language or environment we are trying to solve for a probability in. That is going to do it for the first ever Math Monday. I want to thank you so much for watching. I really hope you enjoyed this introduction/refresher to the normal distribution. Feel free to leave a comment if you have any questions or suggestions. Be sure to like and subscribe. It helps us out a lot. It helps us continue to push out content to our Medium, to our GitHub, and of course to YouTube. And be sure to check out quantguild.com. We just launched our first course, Introduction to Python, taking you from zero to hero in the Python programming language. Other than that, I will see you in the next video.